Hi there, my name is Leah Thompson, and I am presenting on Project 10, which is about presenting serious crime rate in the most populous counties in the U.S. And this is for Stats 512 for summer 2020. So, just introduction, we are provided with some extensive information about the 300 most populous counties in the U.S. from the years 1990 to 1992. More specifically, we are given 14 variables about each county. Our specific area of interest here is the total serious crime rates by population. Extensive research efforts from sources such as the FBI and the Uniform Crime Reporting Program have studied the variables that affect crime rates, such as demographics, law enforcement resources, and policies, and that's just to name a few. Although this list is not complete, it does provide several variables that can potentially affect serious crime rates. My specific research questions are as follows. What variables can help us predict serious crime rates by county? And secondly, what specific predictors are the most useful in estimating serious crime rates by county? And then there's a link right here. The data can be accessed through Blackboard, and that leads you to an Excel CSV spreadsheet. Okay, so for this scenario, I will only be analyzing continuous variables as predictors, and we'll further explain this on the next slide. So my strategy to address my research questions is to build a linear regression model that includes the best predictors for serious crime rates, and then use that model to identify the most impactful predictors. So my null hypothesis is that all beta values would be equal to 0, and then my alternative hypothesis is that at least one of the betas will not equal 0, which I will use my model to explore this. Okay, so let's explore this data. The first thing that I did was to look at the data on Excel and, quote, clean it up, since we are not supposed to be using categorical variables. So I deleted all variables that would not be used. This included the identification number, the county name, the state the county was in as indicated by a 2-letter abbreviation, and geographic region. Geographic region classification was numerically categorized where 1 equals northeast, 2 equals north central, 3 equals south, and 4 equals west. And this came from the U.S. Bureau of the Census. All of these variables are in gray because they were not utilized. Next, I looked through all of the continuous variables to see how their values were determined. Since the total personal income variable was determined by the per capita income variable and the total population variable, I decided to remove the total personal income variable as well. You will also see that this is grayed out since it is not used. Then I decided to clearly identify what y, aka the response variable, was. So the rate of serious crime, which is y, equals the total serious crimes divided by total population. So once I did that, I officially had a clean data set that I was ready to upload to R. You will also see that the total population, so including total population, I have 11 explanatory variables, as seen in yellow. This includes land area, determined by square miles, percent of the population between the ages of 18 and 34, percent of population 65 years or older, number of active physicians, number of hospital beds, percent of high school graduates, which is determined by the percent of adults 25 years or older who completed 12 or more years of school, percent bachelor's degrees, which is determined by the percent of adult population 25 years or older with a bachelor's degree, percent below poverty level, percent of unemployment, and per capita income. So next, I assigned values to all of the variables so that I could explore the data quicker instead of typing out each of the variables' names. So first, I just wanted to get a look at the summary of this model to see which predictors appear to have a significant effect on the crime rate, which is Y. I identified significant predictors by looking at the P is greater than the absolute value of T column and found values less than 0.05. According to the summary output, the predictors which indicated a significant effect were X5, which is the number of physicians, X6, which is the number of beds, X9, which is the percent below poverty, X10, the percent unemployment, and X11, per capita income. After this, I made a mental note just to pay extra attention to these variables as I moved forward, as they could be helpful in building my ideal model. So I continued my preliminary analysis by checking my assumptions, which are normality, linearity, and constant variance. My preliminary analysis, of course, included all of the predictor variables. By looking at the normal QQ plot, it appears that the model tends to follow a normal pattern, more or less. However, there are some extreme outliers, namely 0.1 and 0.3, that look like they could be affecting the normality assumption. So I'm just keeping that in mind. And since I am skeptical, I conduct a Shapiro-Wilk normality test where the null hypothesis is that the data is normally distributed, and the alternative hypothesis is that the data is not normally distributed. The result gives a p-value much lower than alpha, which is 6.526 times 10 to the negative 11, which means that we reject the null hypothesis that the data is normally distributed. So this confirms that the normality assumption is violated. For the constant variance assumption, I was pretty sure, based off the individual Pearson residuals plot, that this assumption would be violated. I couldn't fit all of them in this slide, so basically I just provided a few examples, which is the picture on the right. I've encountered mixed results with the Brown-Forsyth test in the past, so this time I decided to use the Roche-Pagan test, where the null hypothesis states that there is constant variance and the alternative hypothesis states that there is non-constant variance. The results again gave me a much lower p-value than alpha, which means that we reject the null hypothesis of constant variance, meaning that this assumption is violated as well. Now, by looking at this residuals versus fitted plot, we can see that the ab line looks like it could follow a linear pattern, but then it kind of takes a nosedive and begins to slope downwards. Personally, I think that this is just because there are some influential outliers affecting this, so I predict that this model does follow linearity. So, in short, the normality and constant variance assumptions are violated with this current model. Right, so this original model, like I said, has some issues. 5 predictors have been identified as significant, which is not all of them, and our constant variance and normality assumptions have been violated as well. So the first thing I would do to make improvements to this model would be to transform y through a box-Cox plot. After running this, we get a lambda value of 0.5, specifically 0.5151. So this means that our transformed y is going to be equal to the square root of y. After conducting a normality test on this transformed model, the p-value did increase quite a bit to 0.01415. So while this is encouraging, it's still not greater than alpha, so I knew that I would have to eventually come back to this.